Hi everyone and welcome back. Previously we explored how to produce electronic circuits to fully supply a yellow and a red belt using assembling machines of type 1 and 2. Today we'll dive into producing a single blue belt of electronic circuits capable of transporting 45 items per second using type 3 assembling machines. We'll use the same design as with the red belts, featuring 3 assembling machines for copper wires and 2 assembling machines for electronic circuits. To determine the throughput, we divide the assembling machine's crafting speed by the crafting time of the electronic circuits. With a crafting speed of 1.25 and a crafting time of 0.5 seconds, the throughput comes to 2.5 items per second. This means it produces one additional item per second compared to a type 2 assembling machines. As a result, we'll need 18 assembling machines producing electronic circuits to fully supply a single blue belt. To determine the number of assembling machines needed, we simply divide the target production rate of 45 items per second by the production rate of each assembling machine, which is 2.5. To maintain a consistent throughput, we must also ensure an adequate supply of the required resources. Producing an electronic circuit requires 1 iron plate and 3 copper wires. Since producing 3 copper wires consumes 1.5 copper plates, we'll need a total of 67.5 copper plates and 45 iron plates per second. The required resource quantities and the consumption rate of the assembling machines for these inputs also determine the number of input belts needed to supply the resources. The production rate of an assembling machine is 2.5 items per second, meaning it consumes 2.5 iron plates and 7.5 copper wires per second, which translates to 3.75 copper plates per second. A blue belt can transport up to 45 items per second. By dividing 45 by 3.75, we find that a maximum of 12 assembling machines producing electronic circuits can fully utilize the copper plates from a single belt. In contrast, if we were using belts to supply copper wires instead, each copper wire belt could only support up to 6 assembling machines. To transport items between belts and assembling machines, we rely on inserters. The type of inserters used depends on different factors, such as the number of items it can carry at a time. For this setup, we will use a combination of fast inserters and long-handed inserters. Now let's calculate the power consumption of this setup. Two types of devices consume power, the assembling machines and the inserters. Each assembling machine consumes 388 kilowatt. We need 18 assembling machines for the electronic circuits and 28 for the copper wires. This results in a power consumption of 6,984 kilowatt for the electronic circuits and 10,864 kilowatt for the copper wires. Adding this together gives a total power consumption of 17,848 kilowatt. On the inserter side, different types have varying power consumption rate. For the electronic circuits, each setup includes 3 fast inserters consuming 59.3 kilowatt each and 1 long-handed inserters consuming 21.4 kilowatt. For the copper wire assembling machines, there are 28 fast inserters in use. In total, the 82 fast inserters consume 4,862.6 kilowatt, while the 28 long-handed inserters add up to 599.2 kilowatt. This brings the total power consumption of all inserters to 5,461.8 kilowatt. When combined with the power consumption of the assembling machines, the total power usage for this setup amounts to 23,309 kilowatt. Assembling machines also contribute to pollution. Calculating the total pollution is straightforward. We multiply the pollution produced by each machine by the number of machines. With 46 machines producing 2 pollutions, the total pollution output is 92 per minute. Let's now look at the copper plates production. To produce copper plates, we need 67.5 plates per second to supply the 1.5 belts required to produce 135 copper wires per second. Since each electronic furnace produces 0.625 copper plates per second, we need a total of 108 electronic furnaces to meet this demand. Each belt can carry up to 45 items per second, and with each furnace producing 0.625 plates per second, a single belt can support up to 72 furnaces. To accommodate the 108 furnaces, we'll need at least 2 belts. Each electric furnace consumes 186 kilowatt, and with 108 furnaces, the total power consumption for the furnaces is 20,088 kilowatt. For the inserters, there are 2 yellow inserters per furnace, each consuming 15.1 kilowatt. By multiplying 15.1 by the number of furnaces 108 and 2 inserters per furnace, we get a total power consumption of 3261.6 kW for the inserters. This brings us to the total power consumption for both the electronic furnaces and the inserters. For the electronic furnaces, we have 20,088 kW plus 3261.6 kW for the inserters, so together they consume 23,349.6 kW. The pollution will be 108 given that each furnace produces one pollution and we have 108 of those furnaces. In order to produce copper plates, we need to produce copper ore, and to meet the production's demands for the electronic circuits, we need 135 electric drills to mine the copper ore. This will require 2 belts to carry the necessary amount of resources, and the total power consumption for the drills is 12,150 kW, as each drill consumes 90 kW. Each electric mining drill also generates 10 pollution per minute, so with 135 drills, the total pollution output per minute is 1,350. To produce iron plates, we need 45 plates per second to supply one belt of 45 items, which is required to produce 45 electric circuits per second. Since each electric furnace produces 0.625 iron plates per second, we need a total of 72 electric furnaces to meet this demand. Each belt can carry up to 45 items per second, and with each furnace producing 0.625 plates per second, we can fit up to 72 furnaces on a single belt. This means we can transport all the iron plates produced on just one belt. The 72 electric furnaces each consume 186 kW, resulting in a total power consumption of 13,392 kW for the furnaces. For the inserters, each furnace requires 2 yellow inserters and each inserter consumes 15.1 kW. With 144 inserters, the total power consumption for the inserter is 2,174.4 kW. When we add the power consumption of the furnaces and the inserters together, the total power consumption comes to 15,566.4 kW. Regarding the pollution, each furnace produces 1 pollution per minute, therefore the total pollution from the iron plates production will be 72 pollution per minute. For the iron ore production, it's very similar to the copper ore production. Each drill consumes 90 kW and produces 10 pollution per minute. To meet the demand, we need 90 mining drills. Therefore, the power consumption is 8,100 kW and the pollution is 900. If we compare the pollution production and power consumption to the previous version of this design, we can see that the pollution has increased by 40% with a pollution of 2,522 and the power consumption has increased by over 50% with a consumption of 82,475 kW. That requires 1,375 solar panels or 92 steam engines or 15 steam turbines.